So far, we have seen that a large class of periodic signal can be represented with the help of a linear combination of harmonically related complex exponentials. In fact, the representation that the Fourier has given for the continuous time case or the discrete time case was well known to the scientists Lagrangius or Euler decades before the invention of Fourier series. The Fourier series representation for continuous or discrete was not the major contribution by the Fourier. In fact, it was the extension of Fourier series for the aperiodic signals that was the major contribution by the Fourier. So far, we have said that a large class of periodic signal can be represented with the help of Fourier series. But now we are going to extend the theory of Fourier series to the class of aperiodic signals, and that is going to be the most useful entity that we are going to use all during this course. We see that most of the signals that we deal in practice are aperiodic in nature. So let us derive the Fourier representation for aperiodic signals, and that in fact was the major contribution by Fourier. For the same, let us consider the periodic signal as shown on the screen. We can see that the signal that is shown on the screen is xp of t. I have represented that signal as x tilde of t, this signal here. This signal is periodic. You can see that you can take any signal. So I have chosen this shape. This can be any signal, let it be a cos or a kind of triangular or kind of a square wave signal. So this signal is repeating after a period, say t or t naught, you can say. As this signal is periodic, you can represent the signal using the Fourier series representation. Now our aim is to make the same representation or a similar kind of representation for a periodic signal. So in order to differentiate between the notation, I have used this x of t as the signal that is aperiodic. You can see that this signal that we say as aperiodic or that is not periodic in nature can be considered as a signal that is periodic with a period t tending to infinite. What I mean to say here is that, let's suppose if I have a signal x tilde of t which is periodic with the period of t, capital T, then we can obtain the aperiodic signal if we make this capital T tending towards infinite. So this is going to tend towards infinite. Now if I try to do that, these replicas or the copies of the signal is going to be there tending towards infinite, and hence we can obtain this aperiodic signal that is x of t. So if we try to impose somehow the constraint of capital T tending towards infinite in the Fourier series representation, we may get a representation for a periodic signal that is x of t. We're going to do the same with the theory of Fourier series, and we are going to derive the Fourier representation for the aperiodic signal, and that is going to call as a Fourier transform. Let us look at the derivation of the Fourier representation for this aperiodic signal x of t. To begin with, let's start with the Fourier series representation of this periodic signal, and we know that the Fourier series representation of this periodic signal is given by, so this periodic signal, that is xp of t or x tilde of t here, is given by, so this x tilde of t, that is a periodic signal. We know that using the Fourier series representation, as this is a continuous time case that I am considering here, we know that that is going to be equals to summation, where this k is ranging from minus infinite to infinite. Just because this signal is continuous time periodic, this is going to be a k e power j k omega naught, capital omega naught times t. This is the Fourier series representation of periodic signals, continuous time periodic signal, and we know this omega naught is the fundamental frequency, that is 2 pi by t naught, where t naught or t here is the period. So I'll represent that here. I'm considering this as t naught, so this signal is periodic with the period of t naught, that is the fundamental period. Now let us start our derivation using this equation for the Fourier series representation. Now we know what is this ak here. This ak, I'll write that, so I'll make some space here. We know this omega naught, I'll write it here. This omega naught is 2 pi by t naught, and this ak's are the Fourier series coefficients that are given by 1 upon t naught integration over a period of t naught. So let's take that integration over a period, say from minus t naught by 2 to t naught by 2. I can take any period as such, t naught by 2 x tilde of t e power minus jk omega naught t dt. Now as we can see from here that now we want the expression for this x of t. That means we want the expression for this aperiodic signal x of t. However, we do have the expression for x tilde of t. So this x tilde of t, that is the periodic signal, is represented as this harmonically related complex exponentials. Now we know that this aperiodic signal can be obtained when this t naught tends to infinite. Now if we observe these two signals carefully, you can see that this integration is considered over a period of t naught. So from here minus t naught by 2 to t naught by 2, you can see that the signal is exactly equals to the signal x of t. That means I can replace this x tilde of t with x of t, just because these two signals are equal. These two signals are equal between a period of minus t naught by 2 to t naught by 2. So the ak's are going to be, this ak is equals to 1 upon t naught integration over this t naught t naught by 2 to t naught by 2, and instead of this x tilde of t, I am going to write x of t, as both of the signals are same within the period of t naught, minus jk omega naught t dt. Now as this signal is x of t, now I can get this limits extended from minus infinite to infinite. As we can see that this signal x of t is defined between certain limits and it is 0 otherwise. So I can always extend this integration, that is minus t by 2 to t by 2 to minus infinite to infinite, just because it doesn't matter, because this x of t is defined only over a small period or only over a small duration. I can write this as equals to 1 upon t naught. So it's not a problem if I define it as integration from minus infinite to infinite minus jk omega naught t dt. So it's the same thing, because this x of t is defined only over a certain interval and rest of the time it is 0. So I am simply extended the limits of this definite integral. Now we are going to have a short form notation for this a case that we have obtained it here. So in order to do that, this integration I'll represent it with certain notation as capital X of k omega naught. You can see that this integration is a function of this k omega naught factor here. So I've indicated that with this integration, I've indicated that as capital X k of omega naught. So this is going to be equals to capital X k omega naught by capital T naught here. And now this is the short form notation that we'll be using. Now I'll be replacing this ak in the original equation here. This the equation for the Fourier series representation. So I will write a tilde x tilde of t equals to, you can see from this equation that is going to be summation where k is running from minus infinite to infinite ak, and we know this ak from here, it is capital X k omega naught by t naught times e power jk omega naught t. Now this t naught, we know this t naught is 2 pi by omega naught. I can replace that as this t naught is 2 pi by omega naught. So the expression is going to be x tilde of t is equals to summation k running from minus infinite to infinite. So that is 1 upon 2 pi being constant, I'll take it outside, times, you can see that this t naught is being replaced by this 2 pi by omega naught. So 2 pi will be there in the denominator. I have taken 1 upon 2 pi outside, and what we are left with is omega naught here in the numerator. So that is going to be equals to capital X k times omega naught times omega naught e power j k omega naught t times omega naught. So I have simply replaced this t naught by 2 pi by omega naught. Now let's observe this expression very carefully. This is this capital X of k times omega naught can be considered as a kind of function of k times omega naught. That means if I try to plot this capital X of k omega naught, it is going to be something like a function of k omega naught. So I can draw it as something like this. Suppose I have this as capital X of k omega naught, where this k omega naught is on the horizontal axis, that is independent variable, that is k times omega naught. And we can consider this capital X of k times omega naught as a kind of function of k times omega naught. And we can see that as this omega naught is a kind of a fundamental frequency, and this k being an integer, this is going to be a discrete function of this k times omega naught. So instead of drawing this as this continuous entity, I'll draw this as a discrete entity. So this is going to be, say, let's say here, there. So these are the k values. You can say that these values are for different keys. So for example, if this is for this value here is for certain k omega naught, then this is going to be the value for k plus 1 times omega naught, and so on. So these are going to be discrete in nature. Now at this omega naught is 2 pi by t naught, you can see that this omega naught here is 2 pi by t naught. You can see that this omega naught is 2 pi by t naught, and we say that as this t naught, you can see that from this figure here, as t naught tends to infinite. Now why we are doing so? Because we need to obtain this aperiodic signal, and in order to obtain this aperiodic signal from this periodic representation, we need to make this t naught, or the period of this periodic signal, tending towards infinite, because in that case these replicas of the periodic signal will be at infinite, and we are going to obtain this aperiodic signal. So we are observing now what are the changes that are going to happen in the equation if this t naught tends towards infinite. You can see that as this t naught tends to infinite, that means this k times omega naught is going towards 0. So we can see that this t naught, as it goes to infinite, this omega naught tends towards 0. That means this, as t naught increases, this omega naught decreases. So this becomes infinitesimally very small and small. What does that mean? This omega naught, that is a kind of the fundamental frequency, the k times omega naught is going to be smaller and smaller as t naught is going towards infinite. We can say that as this omega naught becomes smaller, this k times omega naught is again going to be smaller. That means the gap between these two subsequent samples are going to be less. They are going to reduce. It's going to reduce. So what I mean to say here, that this gap here is going to reduce, is going to merge. These 2 points are going to merge, as this gap is going to reduce as t naught tends to infinite, because in that case this omega naught tends towards 0. And if this gap tends to merge, this variable, that is k times omega naught, is then going to be a continuous variable. What I mean to say here is that this k times omega naught is going to take a shape of continuous variable, let that be omega. Why is that going to happen? Because we see that as t naught tends to infinite, omega tends to 0, and as omega tends to 0, the gap between these two discrete samples is going to decrease, and as it tends towards 0, the gap tends towards 0. This variable k times omega naught is going to take a shape of a continuous variable, let that be omega. That means this summation is now going to take the shape of integration, because this is going to be a continuous variable. This k omega naught is going to be a continuous variable, And we know what is going to happen if t naught tends to infinite. This x of t, that is periodic signal, is now going to be aperiodic in nature. That means that is going to be x of t. So I'll write it as t naught tends to infinite, that means omega naught. This implies that omega naught tending towards 0. So this k omega naught becomes a continuous variable. Let that be omega, so that is continuous. So the result of this is that summation goes towards integration, because now there is no discrete form of k omega naught. It has taken the form of a continuous variable, and therefore we have to replace it with an integration here. So the resultant expression is going to be as this t naught tends to infinite. We know that this x tilde of t and this x tilde of t is going to be equals to x of t. So this is x of t equals to 1 upon 2 pi. Now the summation is going towards integration, minus infinite to infinite capital X of this new variable, that is continuous variable, let it be omega e power j times omega t times this omega naught. Now we know this omega naught is going to be very small, this is going to be very less. That means this omega naught and change will be this omega naught is going to be d times omega, very small, d times omega. Now this is the expression that we have obtained for the aperiodic signals, and this expression that we have obtained is called as the Fourier series representation of aperiodic signals. So this x of t, as we have seen, is a periodic signal, and we have obtained this expression by imposing the condition of t naught tending to infinite for the periodic signals. So this expression that we have obtained is called as the Fourier transform expression, and the expression that we have denoted here, that is x of omega, that is integration of minus infinite to infinite x of t power minus j omega t, is called as the inverse Fourier transform. So let me write that. So this is the Fourier representation of our periodic signals. So as we see that this t naught tends to infinite, omega tends to 0, this omega naught becomes a continuous variable, and this expression that we have indicated, that is capital X of k omega naught, that is also going to change. So let me write that. The expression for x of k omega naught, instead of k omega naught I am going to have this omega, that is going to be integration from minus infinite to infinite x of t e power minus j omega t dt. This is the expression for x of omega, and we have obtained the expression for x of t. This x of t is going to be 1 upon 2 pi integration from minus infinite to infinite capital X of omega e power j omega t d omega. Now this is what is called as the Fourier transform pair. The Fourier transform is simply the extension of the Fourier representation for aperiodic signals. The first equation here is called as analysis equation. This is the analysis equation. As we are decomposing the original signal into its frequency component, whereas the second equation is called as the synthesis equation because we are rebuilding up the x of t from its frequency components. So let's have a quick review of what we have seen so far. We have said that we wanted to derive a relationship or a Fourier representation for aperiodic signals, and we said that an aperiodic signal is simply the periodic signal with a period t tending towards infinite, and we have tried to impose the same condition into the expression of continuous time Fourier series. And we saw that how this frequency component that was discrete in nature, that is k times omega naught, tends towards a continuous variable, that is omega. As t naught tends to infinite, this omega naught tends towards 0, and this discrete components comes more closer and closer, making this k omega naught to be a continuous variable, that is omega. And therefore we have obtained this new two expressions which are called as Fourier transform. Let me write that. This is called as a Fourier transform. Equations, the first being the analysis, whereas the second being the synthesis equation. We'll see more on this in the next module. See you then.